This is the explanation video for homework 2 and the problems that were assigned. So in this first problem, we are deriving a shell bounce in cylindrical coordinates. And the first step we have to identify is that this is an important area, as this will help get these R values correct in the end. So the first big step is a substitution step. And you substitute big Egen for little Egen, A delta R. And then once you get that, you're able to plug it in down here and then divide out by A delta R. And then this division gives you these two derivatives. And so you take the limit as delta R and delta T go to 0, remembering that del Q over del R is equal to del over del R negative Ka dt dr. You substitute that in, and then you remove 2 pi Lk, leaving R in this derivative because you have to take the derivative of R. And in the end, you get this equation for this problem. The next problem is similar, except it's a flat surface. We are still working, except this time we're working in Cartesian coordinates. So we figure out our known values, what we have to find, and our assumptions. And these assumptions help with our balance as we get rid of these two equations for 1D. Then we have no heat generation and steady state. So it gives us our second derivative. So we take our integrals. We get C1 and C2, which gives us a temperature profile down here, after solving with our boundary conditions at x equals 0. And then we're able to use incident radiation and convection, and we're able to solve this problem by plugging in all these numbers and getting an answer. Then as we move on, the next problem was using cylindrical coordinates again, and we're able to use assumptions of steady state and 1D flow, as this really helped to get rid of more terms, 1D, and steady state. And then as you work through this problem and you get your convection terms, you're able to then get a problem for answer for the first derivative, and then you're able to use the first boundary condition to get C1 equal to 0, because at R equal to 0, so C1 is equal to 0. Then you take your integral again, and you use your second boundary condition, and you get C2 is equal to this statement. And then you get your temperature profile down here, and then using this temperature profile, you plug in your values, and you get a final answer. Then finally, we were doing problems with Henry's law. So what we're able to do is just solve Henry, we get our values, and we get Henry's constant from table 14.6 and our saturation pressure from table A9. Plug these into Henry's law equation and solve for the vapor pressure, or vapor of water and air. And we were able to get this value, and then using your Henry's law constant, you're able to see how much air is in water. So you take your pressure of air divided by the Henry's law constant, and it's very, very small, as not much air is expected to be in water. The only point of confusion that are currently still going on is boundary conditions. So like in this problem and the ones before it are boundary conditions and how to find them and how to correctly apply them.